Hello friends, welcome to Bindu Dhadwal chemistry lessons. The topic for today is catalyst and catalysis. A catalyst may be defined as the substance which when present in a chemical reaction accelerates its speed and is recovered unchanged in amount, and chemical characteristics when the reaction is over. The process involving the use of catalyst in a chemical reaction is known as catalysis. Characteristics of catalysis. A catalyst cannot initiate a chemical reaction. It can increase or accelerate the speed of the reaction already in progress. It fails to catalyze a non-spontaneous reaction. Only a small amount of catalyst is sufficient to catalyze a particular reaction. A catalyst remains unchanged in amount as well as in chemical characteristics at the end of the reaction. It may, however, undergo certain physical changes such as state, color, etc. A catalyst is of specific nature. Different catalysts are needed for different reactions. A catalyst is more effective when it is present in finely divided form. A catalyst cannot change the state of equilibrium in a reversible reaction. It increases the speed of both the forward and backward reactions to the same extent. This is an uncatalyzed reaction. With the help of catalyst, an alternate path is provided. The activation energy for uncatalyzed reaction was more. Because of alternate path, the activation energy decreases. But in the backward direction also there is a decrease in activation energy by the use of catalyst. So it does not alter the equilibrium, it only fastens the reaction. The equilibrium point is not disturbed. It is achieved in lesser time. The equilibrium is achieved in lesser time as compared to uncatalyzed reaction. There are some substances which decrease the reaction rate, and these are known as negative catalysts or inhibitors. For example, decomposition of hydrogen peroxide gets retarded in the presence of glycerol or phosphoric acid. Ethyl alcohol retards the oxidation of chloroform to phosgene. Ethylene glycol decreases the rusting of iron. Role of activation energy in catalyzed reaction. You can see that the activation energy decreases because of the presence of catalyst, but it decreases to the same extent in the forward as well as in the backward direction, so the equilibrium point is not disturbed. Next is homogeneous and heterogeneous catalysis. Catalysis of two types. If the reaction mixture and catalyst form a single phase, then the catalysis is called homogeneous catalysis. That means that the reactants, products and the catalyst are in the same state. For example, sulfur dioxide, oxygen, nitric oxide and sulfur trioxide all are gases. So this is homogeneous catalysis. Similarly, hydrolysis of sucrose involves all liquids, and decomposition of acetaldehyde to methane and carbon monoxide in presence of iodine vapors is also a homogeneous catalysis. Theory of homogeneous catalysis, it is based on intermediate compound formation. So it is called intermediate compound formation theory. This, one of the reactant A will combine with catalyst to form an intermediate compound. The intermediate compound will then combine with reactant B to form product, and catalyst will be freed. For example, if we are to oxidize sulfur dioxide in presence of nitric oxide, then the reactant oxygen reacts with catalyst nitric oxide to form nitrogen dioxide. The nitrogen dioxide intermediate compound then reacts with sulfur dioxide and converts it into sulfur trioxide, and nitric oxide is left free. This was homogeneous catalysis. In heterogeneous catalysis, the catalysis process in which reaction mixture and catalyst are in different phases is known as heterogeneous catalysis. For example, in Haber's process, nitrogen and hydrogen gas react in presence of solid iron to form ammonia gas. So, catalyst is in a different phase than those of reactants. Similarly, In the contact process for oxidation of sulfur dioxide, you see that the catalyst is solid platinum. In Ostwald process for manufacture of nitric acid, ammonia is oxidized in presence of solid platinum catalyst. So it's a heterogeneous catalysis. Similarly, in the hydrogenation of vegetable oil to form solid fat or ghee, this nickel that is used as a catalyst is in the solid state. Theory of heterogeneous catalysis. This states that the catalyst surface has free valencies, and reactant molecules get adsorbed to these few of these valencies, and then the reactant molecules, they will form bonds. Here they have adsorbed, here they are forming bonds, intermediate is formed, then the bond formation gets completed and it gets desorbed to form the product, and catalyst is again left free. However, this theory could not explain the specificity of a catalyst. So this has been replaced by modern adsorption theory. So in the modern adsorption theory, the mechanism proposes that diffusion of reactants occurs on the surface of catalyst, then some association between the catalyst surface and reactants, that is adsorption occurs, then chemical reaction occurs on the catalyst surface, then the molecule reaction products dissociate, that is desorb from the catalyst and diffuse away from the catalyst surface. There are substances which destroy or reduce the activity of catalysts by their presence in chemical reaction. These are called catalytic poisons or inhibitors. For example, traces of arsenious oxide in contact process for the manufacture of sulfuric acid reduce the activity of platinum catalyst. Similarly, in Haber's process, hydrogen sulfide reduces the activity of iron catalyst. Barium sulfate acts as a poison for the catalyst palladium in controlled reduction of aldehydes. There are certain substances which are helpful in increasing the efficiency of catalyst. These are called promoters. For example, in Haber's processes, molybdenum increases the efficiency of finely divided iron catalyst. Similarly, HCl promotes the activity of aluminum chloride catalyst and decomposition of paraffins. Chromic oxide acts as a promoter for catalyst zinc oxide in oxidation of methane with oxygen to give methyl alcohol. Important features of solid catalysts. There are two such features, activity and selectivity. Activity is the ability of catalyst to accelerate the chemical reaction. Reactants adsorb on the catalyst surface. The adsorption should be reasonably strong so that the adsorption does occur. But it should not also be so strong that after the formation of products it's not able to desorb. So this decides the activity of the catalyst. For hydrogenation reactions, the catalytic activity increases from group 5 to group 11. Maximum catalytic activity is shown by metals belonging to group 7, 8 and 9. The catalyst is important to such an extent that you see that hydrogen and oxygen both are present in close proximity with each other, but the reaction will not occur unless there is a catalyst. And when the catalyst is present, the reaction occurs so fast that it explodes violently to form water. This was activity. Then selectivity of the catalyst. A particular catalyst may catalyze a specific reaction only, and nature of product depends upon the nature of catalyst. For example, the same reactants, carbon monoxide and hydrogen, in presence of different catalysts form different products. When they react in presence of nickel, they form methane and water. In presence of copper, zinc oxide, chromic oxide catalyst, they form methyl alcohol, and in presence of copper they form formaldehyde. Similarly, ethine plus hydrogen in presence of platinum catalyst forms ethane, but when The catalyst is palladium over barium sulfate in presence of sulfur or quinoline. This is Lindlar's catalyst. Controlled hydrogenation occurs and ethene is formed.